In this video, I will show you how to draw the vector diagram of an alternator when it is loaded with leading power factor load. Leading power factor, that means our load impedance will be either a pure capacitor or a series combination of a resistor and a capacitor. Therefore, if I connect this load impedance across the phase of the alternator, therefore we have to consider additional three parameters: armature resistance, armature leakage reactance, and armature reaction reactance. And you know that this armature leakage reactance and this armature reaction reactance form our synchronous reactance X of S. So when this circuit gets closed, there is a current flow IA in the circuit. So if I apply our Kirchhoff's voltage law in this circuit, this EPH is our no load voltage or generated voltage, and some portion of this EPH will be dropped across this RA, some portion of across this synchronous reactance, and some portion across this load impedance, and the voltage that is dropped across this load impedance is denoted by this VPH. So if I apply Kirchhoff's voltage law, I will get EPH plus VPH plus IARA plus IAXS. See, I have given the vector sign, that means I am taking the phasor component of this voltage drops. So you know that the voltage drop across the resistor and the voltage drop across the synchronous reactance form a voltage drop that is known as synchronous impedance drop. So I can further simplify this EPH with EPH equal to VPH plus IAZS. Okay, now to draw the vector diagram with the leading power factor load, at first you have to take the reference phasor. Here this IA current remains same all over the circuit, therefore I will take the reference phasor IA in this direction, which I have indicated with this red arrow. Okay, now I will draw our VPH here, as this circuit is a leading power factor load. In case of leading power factor load, if we take the VPH in this direction, current IA will be leading by an amount of angle phi with respect to this VPH. See, as here I am taking the IA in this direction, so the direction of IA is fixed, and this voltage VPH has to be lagging by an angle phi with respect to this IA. Therefore, let's say I take this VPH in this direction, and this forms an angle phi. Okay, now after this black arrow indicates our VPH. After drawing VPH, we have to start with IARA drop. Now see, IARA drops will begin from the terminating point of VPH, and its direction will be in the same direction of IA. Therefore, let's say this blue arrow indicates our IARA drop. After that, I will draw our IAXS drop. What is IAXS drop? IAXS drop is this synchronous reactance drop. As this is, so IAXS drop is a synchronous reactance drop. As you know that in a reactor, if we take the voltage in this axis, our current will be lagging this voltage by an angle of 90 degree. So here this IAXS drop is due to the drop due to this IA. Now see, IA is going in this direction, therefore this IAXS will be 90 degree leading with respect to the direction of IA. IA is going in this direction, therefore IAXS will go in this direction to indicate the 90 degree leading of the voltage value. So IAXS will go in this direction. Now if I add the initial point of VPH and the terminating point of IAXS, I will get our EPH. Therefore this AD indicates our EPH. Okay, now I will draw two perpendicular, one from this D point to this IA phasor and another from this B point to this IA phasor. This will be F and this will be E. Okay, therefore see, now we have two right angle triangle. First one is this triangle, the triangle AEB, and second one is AFD. Okay, now this AB represents our VPH, this BC represents our IARA. Okay, now see, this IARA is parallel, equal and parallel to this EF, so I can write BC equal to IARA equal to EF. Okay, after that this CD indicates our IA XS, this BD indicates our IA ZS, and this AD indicates our no load voltage EPH. Okay, now consider this right angle triangle, triangle AEB. You'll see that this VPH produces an angle phi with this IA. Therefore, its horizontal component, the horizontal component of this VPH will be AE, and the vertical component of this VPH will be BE. So I can write AE equal to VPH cos phi and BE equal to VPH sin phi. Okay, BE, this is our vertical component is a sine component, and you see that this BE is equal and parallel to this CF. Okay, now consider this triangle AFD or ADF. As this is a right angle triangle, therefore I can apply our Pythagorean theorem here. Hypotenuse square equal to AD, so AD square will be equal to DF square plus AF square. Okay, AD square equal to AF square plus DF square. Now see that AF is the sum of this AE and this EF. After that I will draw DF. What is DF? DF is the length of this. DF is the length of this. See, DF, CF minus CD. CF, this total length minus this length, CD. CF minus CD. What is AE? AE equal to VPH cos phi. AE equal to VPH cos phi. What is EF? EF. EF equal to IARAC. BE equal to see, this BC equal to EF, so I can write BC equal to IRA equal to EF. After that CF. What is this CF? CF is equal and parallel to this BE, so I can write BE equal to VPH sin phi equal to CF. And what is the value of this CD? CD is IA XS. So if I put the value of all of them, I will get EPH whole square equal to VPH cos phi plus IARA whole square plus VPH sin phi minus IA XS whole square. And if I take the square root in both sides, I will get no load voltage EPH equal to VPH cos phi plus IARA whole square plus VPH sin phi minus IXS whole square. So this is our no load voltage equation for leading power factor load. Okay, that's it. Thank you.